And now we'll move on to testing a claim about a standard deviation or variance. Um, and to do that, we're going to use the chi-square. Now, don't forget that this is this little lowercase sigma is the standard deviation, and the sigma squared is the population variance. We want to keep those straight here in a little bit when we make our test, when we calculate our test statistic, and that notation is again, excuse me, summarized here, and this is in one of the slides, and you can see that from the slides which I have uploaded to our website. The requirements are all met, as I've said before, and now to calculate our test statistic, which is a chi-square, we place the sample size here and subtract 1, and place the sample variance here and the population variance here. Now you may be given, in the question, you may be given the sample standard deviation. If so, you're going to have to square it to get the variance. You may be given the population standard deviation, and in that case you will have to square that to get the variance. If you're given the variance already, that's already squared, so you don't need to square it here. And we will find our critical values from table A4 and use degrees of freedom again, which is 1 less than the sample size. Now, the chi-square values are non-negative, and here's our chi-square distribution, a generic one, sort of. We don't know what the degrees of freedom are here, but here we can see that degrees of freedom change the shape. It draws the larger sample size draws the distribution more and more normal. And in table A4, unlike the z-scores, which show cumulative area from the left, the chi-square shows cumulative area to the right. So we'll have to be careful of that in a minute when we find our critical value. Now our alpha was 0.05, and if we have a right-tailed test, then that's going to be, we're going to use 0.05 as the area to the right. If we were conducting a left-tailed test, though, if the area in the left tail is 0.05, if the area over here is 0.05, then the area to the right is the complement of that, 0.95. So we look at 0.95 in the top of the table. In using both the z-scores and the t-distribution, we can possibly have a negative value in the left, or two different, or two values that would be the same. They'd be symmetrical, but they would be positive and negative versions. The chi-square is not symmetrical, and so we will have positive values in both the left and the right tail, but they will be different. Now let's go to an example here. We have the heights of 10 supermodels listed here, and the claim is that supermodels have heights that have much less variation than the heights of women in the general population. Well, the standard deviation is given here as 2.6. That's what we're testing against. We don't know that that is really the standard deviation, but that's what we're given. 2.6, and so using this sample, we calculate the standard deviation to be 0.77, or rather, sorry, 0.7997395, and the variance to be 0.6395833. And so those are the values we'll use in calculating our test statistic. And so now we go through the first three steps of our hypothesis test. The claim is the standard deviation is less than 2.6 inches. The claim boils down to that. And that is expressed as sigma is less than 2.6. The complement then would be sigma is greater than or equal to 2.6. So our null hypothesis is sigma is greater than or equal to 2.6 because it contains equality. And the alternative is that sigma is less than 2.6. And since we see that the arrow in the alternative hypothesis points left, we're going to be making a left tail test. We're told to use a significance level of 0.01, and as I said, we use chi-square to find the critical values. Now here's our test statistic, and our sample size is 10. There were 10 supermodels here, and so our sample size is 10. So 10 minus 1 goes here. We were given or we calculated the standard deviation to be 0.7997395, and so we need to square that here. We also calculated the variance. We could have put that in here directly and left the square off, but in this case I've put the standard deviation and left the square. And then in the denominator, the population standard deviation is assumed to be 2.6, and so we square that. And when we run all this through, being careful with our parentheses, we come up with a sample statistic, a test statistic rather, of 0.852. Now, what is our critical value? Well, our critical value is found in the chi-square distribution, which I have, right here. No, I don't. Sorry. Got it right here. Now, because this is a left tail test, and oops, sorry, these are the z-scores. I'll get this straight here in a second. It's the next table, not the prior table. Sorry. So because we have a left tail test and our area in the left tail is 0.05, then the area to the right is 0.95. The area to the right is 0.95. Now we have a sample size of 10, and our degrees of freedom are then 9, and I'm sorry, I'm just recalling that we were supposed to test this to a significance level of 0.01. That means that that's the area in the left tail. The area in the right tail is 0.99. And so that means that our critical value is 2.08. The area to the right of the critical value is 0.99, since the area to the left is our alpha, 0.01, and our degrees of freedom are 9, so our critical value is 2.088. Sorry about that little stumble. And so here's the distribution, and here we have the critical value placed, 2.088. And the test statistic, 0.852. And again, this shows that the alpha is all here in this tail. Well, this tells us that we reject the null because we are under the rejection region. And so we reject the null hypothesis. Now, we then go to our flowchart again to state our final conclusion. And we recall that our original claim did not have equality. It did not contain equality. And so we go this way. No, the original claim does not contain equality. And then we ask, do we reject the null? Yes, we do. We rejected the null in this case. So the sample data, our conclusion is worded this way. The sample data support the claim that the heights of supermodels varies less than the height of women in the general population. So that's our test of a claim about a standard deviation or a variance. In this case, it was the standard deviation.